So for anyone who's speaking in this session, so I'll be moderating. I will not read your title. If you'd like to state your title, you can, but people can read it. So feel free to dive right in to save some time.
All right, we're live. Take it away, James.
All right, everyone. So can I just get a quick thumbs up from someone if you can hear me? I think you can. Great. So welcome back to our third speaker session. So hopefully everyone is enjoying the meeting so far. We have 5 talks during this session, and I'd like to just jump right in and I guess pass the virtual mic to Simon Sponberg from Georgia Tech. Take it away, Simon.
All right, great, James. So I think everybody can hear me. It's coming through. Thumbs up. Yes. Good. Okay, great. Thank you. I'm going to share my screen now so that you can see my presentation. You get to just. Oop. All right. So if anyone can't see that slide, say something, but I think we're good. We tested this earlier. So I'm going to talk a little bit today about centralization in locomotion. This is work done with my postdoc, Dr. Isaac Nevlin, who's taken a short leave to go out and work in industry for a bit, but is now back on the job market. So if anyone's interested in this stuff, please talk to me or talk to Isaac. We've been, my lab sort of looks at the comparative neuromechanics of locomotion. We're really interested in sort of coming up with ways to sort of assess the neuromechanical architecture, the principles that different animals use to achieve different tasks. And so we do it quite comparatively, and we're not really so much sort of trying to design controllers for the animal as sort of trying to do more systems identification, right? Trying to understand the dynamics that animals use or that robots emerge from when we add a controller to their dynamics. It's sometimes really hard, of course, to make a model of all of our dynamical systems when we don't even have good models necessarily for contact, although there's new ones coming up, it seems. So what Isaac wanted to do was to ask how centralized is an animal's movement? And we do a lot of work with cockroaches and other insects. So there's been a lot of sort of appreciation that when animals move across different kinds of terrain, they can use different kinds of strategies of control. And there's been a lot of focus on sort of a feedback to feed forward kind of design strategy where you listen a lot to feedback from your sensors, or you sort of set your plan or your model and you go, right? But centralization has been thought to be an orthogonal axis to this organization. This comes from a review by Phil Holmes, Dan Kotichek, John Guggenheimer, and Bob Full, an earlier paper with Bueller. And the idea of this sort of orthogonal axis here is it hasn't been very concretely defined. Of course, centralization has a concrete mathematical meaning. If we talk about like a network diagram, if we have a bunch of nodes, the centrality of the node is a well-defined mathematical concept. But when we talk about it for locomotion, we're meaning something along the lines of how coupled are the distributed elements that are controlling the movement. So in this case, I mean, don't worry too much about the details of these diagrams, the different the different clocks here are supposed to be first and second order oscillators, but you've got, you can have them to the big thing about the centralized to decentralized axis is how much these are coupled to each other. So of course, if we give a model-like structure, if we fit an animal as it's moving to a set of coupled oscillators, for example, then we can define some aspect of centralization using that model framework. But Isaac and I wanted to ask, is there a way that we could assess the degree of centralization that an animal or a robot is moving with without having to sort of adopt a specific model architecture for it? So is there an empirical way that we can measure this and then sort of assess how it changes as the animal changes the strategy or as we do something different with the robot? And this is important because centralization can come either from neural connectivity, right? I can share neural information from distributed elements, or I can mechanically couple them together. In fact, a purely rigid body system is going to be very centralized, right? Because if I do one thing to any part of the rigid body, it's going to affect all the other rigid body parts in a perfectly deterministic way. So what Isaac wanted to do was he decided to take an information theoretic approach to this. And information theory is very good because it's very general, regardless of the types of signals you can use. You can always calculate information, but it doesn't, of course, tell you anything about the content of that. So we're not going to be able to tell you if it's a PID controller or what control signals are important, but we are going to try and be able to assess how centralized do these control signals behave. So we do have to adopt a state representation of our system. So we have our control signals, in this case, EMGs from the legs that we're recording. I'm not going to go too much into the details of exactly which parts we're recording. I don't think the focus of this talk is sort of cockroach neuromechanical control per se. But we can record the electrical activity from the muscles. And then Isaac tracked the 6 legs of the animal. And he could say, okay, well, how much local information is shared between that control signal and the state of the leg that that control signal comes from, in this case, the hind left leg. And then he could ask how much local information is shared between the control signal and some global state representation, in this case, the global phase average of all of the legs. And the advantage of using information now is we can think of information deals with the currency of entropy, right? So entropy is the possible set of states that a signal can obtain weighted by how likely they are to occur. And so you sort of you can represent it by this area or this circle here. So these are the possible different EMG patterns a cockroach leg could send on each stride, just represented as sort of an area. And you can imagine that then there's some area of possible local outputs. And the more overlap between these circles, the more information is shared. And so that means if I tell you what specific control signal went out, how well can you determine what the actual output of the local leg was? So the more these overlap, the more your entropy of your local output is reduced, the less uncertain you are about the outcome. And so this can be a representation of local mutual information. We can also do that for the global state representation. So we can look at the overlap between our global state and the control signal, and the overlap there will be the global mutual information. And Isaac and I posed the idea that centralization then can be thought of as a difference. And since these are in log units, this is like a ratio actually, right? Between the global mutual information and the local mutual information. So when centralization is positive, it means that the control signal tells you more about what the global state of the system is doing. And when it's negative, it tells you more about what the local state of the system is doing. Interestingly, there can also be redundancy here. This can be measured as the measure of what's called co-information. And that's because your local state is going to share some information with your global state. Of course, where the leg is going to determine something about the average state of all of the legs because it's one of the legs. So there's going to be some overlap here. And so that can be captured as a measure of redundancy here, the amount of overlap between those regions. So the nice thing about this is we can make those measurements without having to assume any underlying model. We do need to have a state representation of the system, but that's it. And so when we do this for the cockroaches, we can calculate that for the many cockroaches running over hundreds of steps with sort of natural variation on a sort of low roughness terrain. And what we can see is that there's those EMG signals and the sort of key control muscles we're recording in the leg convey quite a bit of both local and global information. But the key thing to take home from this plot is that the centralization is actually net positive. And this has an important implication that I think demonstrates sort of one of the interesting things that you can come across with this technique. The fact that that value, that white bar right here is positive, means that if I record the activity of an EMG in a single one of the 6 legs, it tells you more about what all of the 6 legs are doing on average than it tells you about what that specific leg is doing. And that's a little weird if you think about it for a second. It's saying, even though the EMG is of course contributing to the extension of the limb, because of how coordinated the response to perturbations are in the system, that EMG is actually telling you more about what all of the legs are doing together than that one leg is from an information standpoint. And so we think that this is an indication. Part of the reason why we did this with cockroaches is they've been thought to be very centralized in their control architectures, and we wanted to test that. So can we make this a little more concrete? Can we say, is this a good measure? And so for one of the other reasons why we did this with cockroaches is this kind of approach has actually been used before to try, these species have been used before to try and assess centralization. This was done by Einat Fuchs and Phil Holmes, where they did a sort of very similar experiment where they tracked all the legs, and then they actually fit the cockroach's 6 legs to a coupled oscillator model. So this is sort of like a Kuromoto model with not fully global coupling, but sort of a network diagram of couplings between the different legs. And Fuchs and Holmes sort of set all of these couplings to be equal to each other. And you can think of each of the legs then as an oscillator that's connected to each other oscillator. And so each leg then I is going to be evolving in time with some phase velocity here. That's going to be dependent on an innate frequency and then some coupling. So if one of the legs gets ahead of where it's supposed to be ahead of this 0.5 phase difference, then the other legs will try to catch up with that. And when they fit models with different levels of coupling strengths, they found that a coupling strength of 79 radians per second tends to sort of best fit the cockroach data set. So that number shouldn't have much meaning yet, but the idea is that there's sort of, from these models, they were able to fit a coupling strength, which is one measure given this modeling framework of how centralized the system is. So for a coupled oscillator model network, the degree of global coupling, it can tell you about how centralized it is. You can also do this with order parameters if you want. So what we wanted to do was to ask, how does that match up with our data? So we took our same approach, but instead of running it on cockroaches, we actually ran it directly on the oscillator model. So we took a coupled oscillator model now with similar connectivity. We added noise and we added a perturbation to it. And so we could play that perturbation and that actually becomes your control signal. And then you could look at the outputs and you could say, how are they related to one another? And as we see the centralization increases with coupling strength, which is what you would expect, right? This is what we'd expect. This is with an undergraduate, Amelia, that was in the lab. But interestingly, our value of centralization that we measured just purely from the cockroach experiments without having to use a coupled oscillator model was this value of about 0.2 bits per stride. And that matches up very well with the coupling strength that Kuz and Fuchs measured when they assumed the sort of underlying coupled oscillator model for the cockroaches. So we get some validation that our empirical measure of centralization can at least recapitulate earlier data. And the last thing that I wanted to sort of show is that this can actually be extended to sort of think of new hypotheses of how the system is working. So we turn to a robotic system. This is the quadrupedal robot Minotaur from Ghost Robotics that was developed by Avik Day and Dan Kodacek. And the cool thing about this model is it has direct drive legs. So the legs are not fully determined by what the motors are doing. They can be back driven. And it has these masses on a boom that stick out from the top of the robot. And by changing those masses, you can change the degree of mechanical coupling in the system independent of the controller. So what you can do is you can spread if the mass is really tight into the middle, then when you apply an impulse to the front set of legs, it's going to cause the back set of legs to move down because the center of percussion, the stationary point around which the robot rotates, is going to be in front of the hips. If the masses are really distributed far out, then the center of percussion is going to be behind, and when the front legs push on the ground, the back hip is going to move up. But there's a point right in the middle where the center of percussion is aligned above the legs. And at exactly that point, the front legs and the back legs are going to be mechanically mostly decoupled. That means they're not going to apply moments to each of the other hips. And so the prediction would be that that should then become the most decentralized point. Independent of the controllers that's being used, we're changing the mechanical coupling now. So Isaac ran our information theoretic approach on this. And indeed, what he found is that just by recording the robot as it's moving around, not by sort of going in and trying to model it anyway, just recording the kinematics of how it was moving using a global and local state estimation, he was able to recapitulate this idea that they are in fact adopting their most decentralized control down here when they're having those legs directly positioned below the centers of percussion. And so altogether, we think that this can sort of be used, this sort of information strategy can be used to think of as a design space here, both for placing animals as they maybe are changing their situations or the environments that they're running through or aging or having some damage or injury, but also for robots. So on the left side here, a robot or an animal would be highly decentralized. That means the control signal primarily determines the local state of the individual limb or joint. On the right side, it would be highly centralized. The control signal is mostly determining the global state. And then on the y-axis, we have the degree of redundancy, going from fully redundant, which would be very stiff systems, to less redundant. And we can put all of our robot, cockroach, and coupled oscillator models on there, and you can see that we can span at least the upper side of this space. And we think that things like very stiff systems that are very rigidly connected together mechanically, it's very hard to sort of do anything different from your local state to your global state. So those systems are actually going to be highly redundant, not either centralized or decentralized. But the sort of classic reflex-based control where you take care of perturbations entirely locally would be a very decentralized architecture, a sort of very model-heavy control where you're primarily doing your control based on some central model of what the global state is evolving in time. That would be highly centralized. And then maybe soft systems actually have this region where there's synergy, where you know something more if you know both the local state and the global state than if you just know them independently. So this whole strategy is we were trying to find a model-free, not state-free, but model-free information-based measure for centralization and redundancy so we could try and assess this broadly in the systems and ask when is centralization good and when is it not. we can recapitulate the coupled oscillator model, and we can show that this actually allows us to capture changes in mechanical coupling in a robophysical model. And so with that, I'll just thank the people in my lab and turn it over to questions.
All right, thank you, Simon. So as before, if you have any questions, please use the raise hand feature. So during your talk, there was a question by Chris. And Chris, I don't know if that your question was answered sufficiently. If not, feel free to jump in and pose your question.
So in this meeting and in the field of neuroscience, we've spent a lot of time trying to figure out what do neural signals actually do.
Yep.
And, you know, especially with the advent of passive dynamic walking, you know, one question is, how would your analysis play out with a passive dynamic walking cockroach? The second is, in neuroscience, usually the attempt is to relate mutual information with certain lags or delays in order to relate or separate out mechanical effects and neural effects. Are you doing that here?
No, so this is one of the things that I think is very important here, is that centralization can come either from mechanics or from neural coupling, right? I think that's the key thing. And in fact, Einat Kuzenfuchs and Phil Holmes sort of touched on this nicely in their papers too. You could have either mechanical coupling or neural coupling that would connect the different components of the system together. So I think it's a little bit different from this feedback to feed forward axis. How much is it relying on passive mechanics versus feedback dynamics? Now, there could be related questions, and you're totally right that information has been used to try to separate these components before. That's not really the strategy we're using here. We do a lot of neuroscience in the lab. I'm primarily an experimental biophysicist. So we've used it to try and sort of match up for delays in other systems and flying systems primarily. But we're, in this case, what I'm trying to suggest is that this is a way of sort of getting a view of how is the emergent dynamics of the combined neuro and mechanical system behaving. So you can imagine if I now just tried to design a controller, right? If the system is highly centralized, it means if I design a controller that's only going to affect a local state that tries to adjust just one limb, for example, that may not be a very effective control strategy because there's so much coupling going on in the system that really what I need to do is design a control strategy that might be more at that affecting some global state. So what I'm mostly using it for in my lab is to try and think of, okay, is this a way that we can assess the performance of the emergent nature of one of these systems, and then say, okay, well, okay, as the cockroach runs faster, for example, does it become more centralized or less decentralized? That was a hypothesis that we didn't have an answer to before. It turns out they don't become more centralized. They keep exactly the same centralization, but they change both the amount of local and global information that each EMG is conveying about the system. So the total degree of coupling is the same, even though you get a shift in how much sort of neural contribution there is to the overall state. Did that answer your question?
I still have many things to ponder, so I'm going to go ponder.
Oh yeah, I'd be happy to chat afterwards too. That's the great thing about these works.
All right, the next hand I saw was from Jonathan Hurst.
Yeah, thanks. So I'm thinking the question here maybe, and please argue with me, is more about the control hierarchy and where the feedback exists. Because on the one hand, you can think about, you know, all these animals and robots too, we're finding you really want a clock cycle, something that's just sending down some sort of a coordination. And then any sort of local controllers down the line are going to try and align with that clock cycle. Or you can do full state control, where you have every piece of feedback, you know, if you move one end of the limb, the other is going to react. And I've heard it for say, a cockroach, you know, if a foot misses the ground, it's swinging back forward before it even registers, you know, centrally that it missed the ground. And so it feels like maybe it's more of a clock cycle moving forward. So the question is, you know, what's the hierarchy? Is this telling us anything about that, or anything about whether this is just a feed forward clock cycle, or whether there's some type feedback with kind of whole body control going on?
No, I think the feedback feed forward question is an orthogonal question to how much centralization there is in the system. And I think I do agree with this sort of formulation that's up on this slide about that. And the important thing is that the limbs can be coordinated from an upstream clock, right? But it's how is coordinated is the response to the perturbation. So the degree of centralization is emergent of the combination of the controller and the plant, right? It's a property of the dynamics of the total system, not of one or the other. You're not separating one or the other. I'm not pulling the controller out of the cockroach and just trying to assess that. This is a property of the system as a whole. And so I think but what you could ask is, does that centralization arise mechanically or neurally? I think that is a really interesting question to ask. And I think you could do that by now, for example, starting to manipulate the mechanical connection, having them run on soft surfaces or something like that, or changing the neural connection, right? We can go in and ablate or add noise to one of the neural signals, and asking how much does that affect the degree of centralization that is emergent of the system. So I'm working it more from the perspective of looking at what are the dynamics that come out. And in this case, we're using an information theoretic framework. Information is not a very powerful signal because it doesn't tell you anything about the it's not a very powerful measure because it doesn't tell you about the content of the signals. It just tells you about how much each of them relate to one another.
You're just asking about how much does information from one corner of the system make it to the other corner of the system?
Well, I'm asking about the relative amount that the control signal makes to the global versus the local. And I'm proposing that this is a nice way to sort of get an easily accessible empirical measurement for how that system is actually behaving. Because a lot of times we might design a local controller, but if there's a lot of mechanical coupling, the whole system might be behaving quite centralized. And so this gives us a way to sort of, I think, to assess this. I'm mostly interested in trying to understand how the animals are behaving when we do in different kind of contexts. And that's sort of where we use this in that space. But I think there are some strong implications that you can have for designing control. But of course, there's a long history of trying to connect information theory to control theory. And it's always a bit of a tricky subject, to say the least, right?
Thanks.
We'll do one more question here from the chat. So Dan Kodacek had a question about weak and strong coupling. Feel free, Dan.
Hi, thanks, James. Congratulations on this very exciting work. I am confused. When Phil set the coupled oscillators thing up around in the mid 80s, when these things were first getting off the ground, the presumption was always, quote, weak coupling, such that these Ks are going to be small enough that it makes sense to do this in the first order sense rather than going to the second order, blah, blah, blah. What I'm confused about is if we have a small, a relatively small K extended phase-based coupling, according to Phil's model, I worry that that's confusable with a sharp stride by stride impulse like control or mechanical event. If that sharp impulse is happening a lot during a stride, then I can imagine these are going to be easily distinguishable. But I worry a little bit that if you only have one sharp event during a stride or two sharp events during a stride of very large magnitude, that also integrates out in the information theoretic ocean. Am I wrong to worry about that, Simon?
No, I think that if I understand correctly, you're saying that what if the system is not well described by a coupled oscillator model and instead has sort of these.
Well, it's a coupled oscillator, but it's a very stiff coupled oscillator, right? So
sure.
Yeah.
Right, it's got these strong mechanical connections, right?
Or neural, it's doing something more like a Raybert Hopper than like an Ulich-Saranli active damping vertical hopping regulator, something like that.
So I think that's a fair criticism of why we might want to be skeptical about fitting a coupled oscillator model to this system. But I'll point out that the information calculation that we did up here doesn't care which one it is, right? This does not. That's in fact, I might say that that's a really good explanation for exactly why we wanted to do this. Is we didn't want to have to assume that it was a coupled oscillator model and that it couldn't necessarily be well described by Ks, because when you have a coupled oscillator model, K, the coupling strengths are that's like the one system where I know how to describe centralization from the literature, right? But we didn't need to do any of this. If we did it, I showed that the outcome here matched up with what our measurement was independently. But our measurement of centralization was purely from the information theoretic approach. And I'm not trying to say that this is the only model that would give us that measurement of centralization. I think it's sort of suggestive that we get to the same conclusion that Phil got to in that paper with Ina. But I think there are a number of different systems that could give us the same kind of centralization. Did that answer?
Someday, Simon, I want you to invent an assay that'll distinguish between intermittent, spiky, or in hybrid systems lingo, guard-like controls versus, smoother. But that you can do that next year. That's okay.
Well, Isaac did do one thing. Let me just say one thing that he did do is he actually, the cool thing with the cockroach muscles is that he can, because these EMGs have distinct spikes in them because there's many fewer motor units, he was actually able to separate out the contribution of the individual timing of each spike versus the overall sort of rate average, which may be the first sort of way of sort of trying to get at a little bit what you're saying. It's saying whether, after this is the big filter of the muscle that is very dynamic itself. So, don't read an EMG as impulsive or continuous, right? That's always problematic. But to the extent that we can talk about the importance of the timing versus the rate of spiking here. And the timing ends up conveying most of the information that goes into the control in this case, not the number of spikes. So this muscle is not behaving like a simple sort of rate controller. Having that. I don't know if that quite gets that impulse, so I don't think I've answered your question fully, but it may be a step along the way.
All right, we still have some questions, but I'm going to go ahead and move on to the next speaker. So as we mentioned in the last session, if you would like to keep the discussion going, you can do that in a spatial chat after this session. Just a quick point for those who maybe are attending the meeting for the first time. If you haven't already heard, we have a tendency to allow discussions to continue somewhat beyond the time that you might expect if people seem engaged. So try to sort of continue that theme today to the extent that we can. So next, I'll hand it over to Chen Li from Johns Hopkins University. And Chen, you may be muted.
Okay.
Okay, there you go.
Yeah, thanks.
We can hear you now.
Thanks for the organizers and everyone for the opportunity to present. So I'm going to talk about our recent work on the energy landscape approach to legged locomotor transitions through large obstacles. We already have many robots, such as self-driving cars, that are really good at navigating complex environment. And what they do is they create a geometric map and then transition between different driving modes to avoid obstacles to reach their goal. There are some applications that we also need our robots not just to always avoid obstacles, but actually traverse them, such as search and rescue in earthquake rubble. And our robots are still not very good at making robust locomotor transitions to do so. And this is partly because we have a relative lack of understanding of physical interaction with complex terrain like this. In the previous animals, obviously, they are very good at using physical interaction to make robust locomotor transitions to traverse all kinds of environment. So in a previous study led by myself, when I was a postdoc, we looked at how cockroaches can traverse dense vegetation, such as grass-like beams, and we found that they transition among many different modes, forming these multi-pathway transitions. So here in this talk, I will give a short highlight of a recent study led by my PhD student, Ratan, focusing on one particular transition between what we call a pitch to a roll mode to reveal how we can begin to understand the emergence of locomotor transitions from physical interaction. So here's the animal doing the pitch mode. It really is the animal just pushing down the beams, in which process its body pitches up slightly. And here's the animal initially tries to push across the beam, but quickly transition to rolling into the gap between the beams. And this is what we call a roll mode, transitioning from pitch to roll mode. So what might be happening? We then came up with the simplest physics model we can think of by ignoring completely the system dynamics and treating the animal just as a rigid ellipsoid, and then two adjacent beams as these plates with torsional springs at their base so that they can bend. So now you can write down the total potential energy of the system, which is the sum of gravitational and elastic energy. And then depending on where this body is and how it's oriented, when it's close to the beams, that's going to bend the beams by a different amount, as well as change the center of mass height. So the total potential energy of the system is a function of the position and orientation of this body. So what's been plotted down here is just the a cross-section of the potential energy landscape over the body pitch and roll degrees of freedom when the body is very close to these beams. And you can see that these three locominima basin, here in the middle, there's one in which the body pitches up slightly without rolling if the system state falls to the very bottom of that basin, which looks like this. And then you see these two other basins in which the body, if it falls to the locominima, it would then roll either to the left or to the right. So you can see that these orientation are reminiscent of what we observe in the pitch and the rolling mode of the animal traversing. So perhaps the locomotor state of the system is attracted to these basins on the potential energy landscape. In addition, for when the animal actually makes the transition from the pitch to the roll mode, it has to overcome these potential energy barriers separating these basins. So perhaps a locomotor transition is a barrier crossing transition. So with this, we were really greatly inspired by another field where people have applied energy landscape modeling to understand protein folding. And this has been really successful in understanding how such multi-pathway transitions emerges from the physical interaction between all these atoms in the protein. And you can see that there's this analogy of our system. So we think maybe this can be a useful approach to understand locomotor transitions in complex terrain. But there's a caveat. For the protein folding, which is a microscopic system, you have thermal fluctuation that's actually helping the system cross these little free energy barriers to make transitions to eventually fold. But for our system, which is macroscopic, obviously thermal fluctuation is not relevant. But if you look at how the animals traverse these kinds of environment, you can see that because of their legged pushing with the ground, they actually oscillate quite a bit. So that might be serving the same function as thermal fluctuation to help them cross potential energy barriers. And to test whether this is the case, we developed a simple robotic physical model, which is free to pitch and roll in response to its interaction with the beams. And then we can push it forward and apply oscillations to test whether that helps. So here on top, you can see as the body pushes in the middle towards the beam, it is stuck in the pitch mode and pushes down the beam to traverse. But with some oscillation below, it's able to quickly find its way to this rolling mode. And when we actually reconstruct the state of the system, as projected on the potential energy landscape that we reconstructed, you can see that in the pitch mode, it is indeed attracted to the pitch basin, but with some oscillation, it's able to escape from that basin and finding the rolling mode. So we have confirmed all our hypotheses, which I won't repeat. I just want to quickly point out at the end that this vibrating like a particle is just one very naive strategy that we have identified. And we have found several other strategies already in multiple systems when we use this approach to understand locomotor transitions in complex terrain. So with that, I will just leave the acknowledgements up, and then thank you all for your attention. I'll take questions.
Thank you. So we're now open for any questions.
Chris.
What's the role of the antenna on the animal if you can just drive the round animal through a square peg or square peg through a round hole or whatever it is?
Yeah, that's a great question. So in our early study, we did some preliminary observation, and when the animal are just simply exploring the obstacles by themselves, they do seem to sweep their antenna a lot to try to detect if there are any gaps, and that seems to help them initiate this rolling transition. In this particular study, because we're focusing on understanding this, how this transition emerges from physical interaction, we're actually pushing the animal to the limit, to the bandwidth limit, where we have a little rod to kind of press their abdomen, and then they get scared and they run really fast. So in this process, we do see that the antenna would sweep as they traverse. We're not sure how much role that's playing, but what I didn't show is we did perform animal experiments similar to our robot experiments, as well as this energy landscape modeling, and we found that their behavior seems to also be qualitatively really well explained by the landscape. So that suggests that at least in this rapid escape response, which is bandwidth limited, their locomotor transitions do seem to be strongly governed by these landscapes.
The next question from Dan.
Hi, Chen. Great, wonderful. In these terrific ethograms that you've been building, as I recall, all of the transitions are characterized by a potential landscape with such a barrier. Is that true? Is there in your ethogram, have you discovered any transition that couldn't be describable potentially in terms of a kinetic energy excitation, or are there some that are much more quasi-static?
Yes, for sure. So here, this is a summary of our previous study, and you can see there are certain modes, such as climbing, that we don't think our landscape can explain.
They don't run, they don't race up, they creep up, they don't race up on the climb?
We haven't, so in this study that we did, the beams are stiff enough so that when they run into it, they're forced to stop. And the more recent study that we showed, in this study, we did vary the stiffness of the beams, but we still focused on understanding this particular pitch to roll transition. So we didn't look extensively at if they can simply run into the flimsy beams and run up. Yeah, I think that what you mentioned, that brings up an important point. We are not claiming that this potential energy landscape can help understand all the possible locomotor transitions in this kind of environment. We are still thinking how to define this, but we think that right now we have a concept of energy landscape dominated regime, and right now we think that it is defined by the fact that during each propulsive cycle, the kinetic energy that you can generate or the mechanical work that you can do is small compared to the barriers that occur in certain directions. So then your movement along those directions would then be strongly dominated by these energy landscapes.
Okay, and then one last question here from Art. Let's see. All right. Oops.
Trying to unmute. Okay. My question is about how literally you mean potential energy, because it seems with these springs, it's not potential energy in the sense that the cockroach is getting it back, right? It's essentially converting that potential energy into motion of the thing wobbling around afterwards. Whereas there's some kind of potential energy that you do get back. You go up a hill, you might be able to slide down the hill. Do you mean an abstract sense of energy, or do you literally mean potential energy, a conservative quantity?
Yeah, we do literally mean a conservative potential energy, and that's how in our model we don't have any like term that's made up or any fudge factor. It's all just directly writing down the total potential energy of the system. But I do want to point out that when we perform these energy landscape analysis, where how the system state behave on the landscape, we can see that it's attracted to these basins, which show up as locomotor modes, and then the transition between basins show up as transitions crossing these barriers. But this is only true in this case. This is only true before the animal has crossed the beams. When the beams have crossed the barriers, the beams will bounce back, and then in that phase we no longer reconstruct the energy landscape. So what does this mean? There's dynamics involved that's after that our model doesn't take into account.
Okay, so if you had a more literally dissipative barrier, say damping, then would you still render that as potential energy?
I think so, but I think we would then, if you really want to understand the dynamics, you would have to then add dissipative terms. Let me show one slide. It's not directly addressing that specific question, but sorry, somehow stuck. Just real quick here. Yeah, so yeah, that's the limitation of a major limitation of our model. It doesn't have any dynamics, but we recently begin to think about how we can build upon this. So this potential energy landscape only takes into account all the conservative force in the system, but you certainly have propulsive forces and dissipative forces that are not conservative. So this is just a very preliminary modeling. So here's what I didn't show, but here are many trials in which the animal either are stuck to the pitch basin or to the pitch mode and transition to the roll mode. So we can actually make up force terms that describe non-conservative forces, such as this drag here, and you also have random force, and then write down, basically use Newton's second law and write down the Langevin equation to perform a dynamic simulation, and you can see it does qualitatively give you the behavior that we observe in the experiment, but we're still very far from knowing how to exactly model all these terms are made up. Yeah, but that's what we are thinking of working on next. Yeah.
All right, well, thank you, Chen. And with that, we will we'll move on to our next speaker. Right. So our next speaker is Turner Topping from the University of Pennsylvania.
Hey guys, can you hear me?
Yes.
Hello, everybody. Okay, perfect. And then you can see the slides on the screen. Great. So yeah, my name is Turner Topping. I'm from the University of Pennsylvania in Dan Kodashek's Code Lab, and this is our extended abstract templates for transitional leg behaviors. So, oh, good. We got to get back into this, don't we? Can I proceed? There we go. Perfect. All right. So transition. What do we mean by transitional legged behaviors? We'll just start by showing you a few examples. So you know, this is a behavior in which we do some kind of brachiating thing and transition into a leap and then back into another brachiating thing. Here's a transition where we go from kind of a walking regime into some kind of fence climbing behavior. And finally, here's one where we're going to try and manipulate this stool and move into this kind of stool pushing regime. So you know, this is already 3 different applications in 3 examples, and this is 3 different environments in 3 different examples. So, you know, you can imagine that the space of transitional things is going to be really large and, you know, really specific if you're making up a new controller for each one of them. So what we really want to do is avoid rewriting things for these new situations and instead kind of recycle the pieces that we find to be common. And so the key is to find these common elements between them and figure out how to compose them. And I guess I mean this in the hybrid dynamical system sense. You know, we can compose them either in sequence, one element follows another, or we can compose them in parallel, you know, when possible. Maybe we can do kind of 2 things at once with the robot or platform. But, you know, there's some challenges to doing this. And one of them, and probably the one that we're most focused on right now, is getting some kind of formal guarantee for each one of these elements. So this looks like, you know, a Lyapunov function or a basin in kind of the world that we're thinking about. And the main reason for this is when you go to compose these things, you know, these behaviors are very one way. And if you make a mistake, or if you're going to make a mistake, if you're doomed, you want to know when is appropriate to stop trying to do the, you know, compose transitional behavior and when to do something else, because you know that the next thing that you're going to be trying to do is inevitably going to fail. You know, we're also going to rely a little bit more heavily on the underlying models. A lot of, you know, reactive control prides itself on being robust to perturbations in the model, but again, due to this kind of one-way nature, you know, we're doing a lot of deadbeat-like things, if not deadbeat things themselves. We want to, you know, be able to rely on our model a little bit more than we have in the past. And finally, you know, this is the last key here is finding a common medium of exchange. What quantity can we measure that's going to link up these seemingly disparate pieces of transitional behaviors in a way such that we can reason about creating what we call in hybrid dynamical systems literature guards and resets that make sense. So we'll start to talk, you know, specifically about this this work here, which is opening a door, and this is really similar to something that we did back in 2017 in terms of the way that it's composed. And so we'll actually just jump right into that. And so I'm just going to show this very simple diagram here. there's this first moment here where we're injecting energy to the system. And actually, I'm really happy that Chen Li just went before me talking about these barriers. To operate in mode C, you need to overcome this literal energy barrier that you start out in mode A. So you need to kind of inject energy, you need to excite the system. And then once you've added the energy, you need to handle it in a way that you wind up in the configuration that you expect. And so we kind of mimic a pendulum dynamics here. Then once you've done that, you can do that leap toward the door. And once you're airborne, try and figure out how to handle the doorknob. We're not even going to focus on that here. But so here's kind of a frame by frame or a composite image here of the kinds of things that we're doing. And so mostly we're going to focus on the two parts here is how we transition from this first kind of ghostly looking image to the one that's first vertical, and then from that one that's actually, or the one that's vertical to the one on the doorknob. And in the past, we did this by, kind of carefully tuning the system, recognizing that we knew something about the states, something about what the guard conditions look like between, A and B and C, but not really having a formal way of understanding it, nor did we have any hope of kind of adjusting to significant perturbations that our robot was experiencing. Maybe we added a sensor payload or something like that, and we didn't know which way to kind of tune these numbers. So what we've done here is we've decided to, again, taking that same structure, that ABC structure here, and instead start to apply templates to them. And so we'll just kind of, this is the only one that we're not really going to talk about formally, but we can imagine the toe as being a point particle manipulator. We like to think that the legs are massless, so we can pretend that this is just a first order dynamical system with some workspace. And so the whole point of this behavior is going to be driving the workspace around to get this close enough to the point where it can manipulate the doorknob. So how do we do that? So first, we've got a template that we introduced recently called this pinned hip template. And it's really nothing more than trying to keep one of the hips fixed in the world frame so that we can treat the body of the robot like a pendulum. And then we get these nice pendulum dynamics. And at first, when it's active, when we're injecting energy, we get this control input U. And so we're just trying to, kind of excite the system to the point where we have literally some amount of joules in it that we're okay with to move on. And we'll see kind of what I mean by that in a second. But once we have an adequate amount of energy in the system, we just keep behaving like this template, or sorry, like this pendulum. So this is now, the dynamics have no input control. And the reason for this is because we're able to make some kind of prediction here with a 1 degree of freedom system. If you're adding energy to a 1 degree of freedom system and you're not, losing it, it's not leaking out in other places, you're going to be able to kind of understand in the future when you have more potential energy, what you're going to be able to do. And so that allows us to predict, the kinds of conditions that this next piece, the floating torso piece, and I regret that I won't be able to really go into any kind of detail about this at all, but it's basically an idea that you can sort of separate the pitch control from an underlying inverted pendulum-like template. And what we want to get are some kind of formal properties about when you can start using this template, under what conditions. And if you can do that, empirically we have some idea, but we want formal analytical conditions that we can sort of predict back in that first step. And so then once you've done that, you can then use this new template to kind of regulate the pitch through the leaping phase, which is something that was a cause of a lot of failures when we were doing this years ago. And so now we can actually kind of see these results. And the things I want to point out are, one, we have actual feedback control going on sort of within stride, if you think about the leap being a stride, on the body pitch. It's a very short amount of time. It looks like it's 0.2 of a second or a little bit less. But where you can actually kind of see that the velocity, not damping out quite at the rate that we'd like, is at least staying somewhat regular, and again, empirically is going to be good enough to allow us to kind of do this door opening thing pretty reliably. The other thing I want to point out on this chart is that, again, we have that energy condition that kind of sets up this feedback controller for the floating torso. And, even with a kind of bad estimate of energy, this is really laggy due to the kind of laggy and noisy estimates from our IMU, we're still able to kind of dial this in. And if it works well, energy is this isn't going to be mass specific, right? We're looking at sort of velocities and positions in pitch. And so we don't have to worry about kind of perturbations to the system in that regard. So in concert, we're hoping that these kinds of things allow us to have a much more robust behavior. And there's still room to improve. Obviously, we're not doing anything in this passive pinned hip phase here. We're just kind of coasting until it's okay to start the next one. And what we'd like to do is start adding feedback there too, because it might be the case that after you've injected energy, some adversary comes by and bumps into your robot and slows it down. And you'd like to be able to, if there's anything you can do, start to feedback on that situation. And if there isn't anything you can do, start to change the sequence, change into a different template that's more appropriate. It maybe abort the behavior or try something different altogether. So I'm trying to keep this to the 5 minutes. So I'll say one more thing actually before I jump to the questions. So ultimately, when we build these kinds of behaviors, how are we going to use them? And this is kind of what the key about these, understanding these basins and having these formal regions, or sorry, formal Lyapunov functions around each one of these templates. What is going to be the unifying principle to control them, to assemble them? Is it that point particle manipulator? Can we describe it in such a way that the desired motion of a point particle in space can inform some smart controller to how to assemble these templates in a way that we can track it well? Or is it some kind of unicycle that has these extra features, a unicycle that's able to jump or something like that? I don't know. It's difficult to imagine what the right kind of unifying structure is, but it's also exciting to even get to think about this at all. This is the first time in my career that I've been even close to having this problem be the next one up. So it's been very exciting. All right. So with that, I'll turn it over to questions. Yeah, thank you very much for listening.
All right, thank you, Turner. So given the schedule, we have time for maybe one question here. Looks like Simon Sponberg has a question. Go ahead, Simon.
I was just curious how you choose the sort of granularity of when we do these transitions from one template to another versus when we think of it more as a continuous thing. So I've always had this question of, for behavior, how do we think of behavior as this continuous thing or as a sequence of discrete circumstances or certain discrete cases or discrete models that are working. So in this case where you're working on it, you're doing these transitions between the different templates. Do we always have to cut it up in this? How do you know where to cut it up versus trying to make one model that encompasses both of the sides of the transition, is I think the concise way to ask it.
Yeah, that's a very good question. So obviously I've been, as the designer of this behavior, I just picked a sequence that I thought might work. And I've been kind of, using that. But to my point earlier about having the right coin of exchange, the, energy is something that seems kind of like a good medium of exchange, since it, remains continuous throughout the hybrid mode of the behavior, right? So that's something that allows us to kind of think, reason about these transitions, but that's not going to be enough. And the other kind of way to answer this question is to, an anchor is an anchor that doesn't change. If you think about, the links of the robot, you have some kind of highest degree of freedom model that you choose to represent it with. That's not going to change regardless of the template that you try to anchor to. And I apologize for using this language for those of you who are unfamiliar with it. But the idea then would be, you could try and sort of imagine two different templates at once and see what's going on in either one of them. And if you had a right measure about, the kind of difference between, good or bad, is it good to be template A or good to be template B at this moment in time, you might be able to kind of switch more fluidly in a way that's more reactive to what's going on. So, this is kind of getting at the idea of, do you switch into the single stance leap or not? You could imagine that you've already done it and you can see where you fit in that template state space. And if you're not in some basin, then you won't do it, right? Like, or maybe the distance from the edge of that basin is something that you might factor into these sorts of things. So. Does that answer your question? Sorry, Simon.
Yeah, I think that's right. It's sort of like, how granular do you make your template? So when a template fails to describe the behavior, do you make another template and add a transition between the two? Or do you just use a more anchored model that can connect both, that can encompass both of the templates?
Yeah, I don't know the answer, but that's a very good question. Yeah.
All right, so thank you, Turner, for the great talk. And again, we can continue discussions in our spatial chat room later. So with that, I'd like to introduce our next speaker, Robert Griffin, who's going to tell us about some of the work being done at IHMC.
Thanks for the introduction, James. So some of the things that we're really interested in at IHMC is actually trying to make some of our robots a little more useful. So let's see. So one of the things you could think about doing with a robot like Atlas is use it to be able to get across rough terrain, then actually which we're kind of replicating here with cinder blocks. If you are willing to believe that that's rough terrain. And then be able to clear some debris out of the way and then be able to get to its goal, which in this case is that blue barrel. So in this specific example, we're actually using the robot in order to perceive the environment with its LiDAR, build a model of it, and then the operator is using a footstep planner in order to navigate across. And then it's also using this virtual reality interface in order to teleoperate the robot to clear this debris. But we'd like to kind of speed up this whole process. And so, because it's not quick enough, and one of the biggest parts of that is actually just this time that it takes in order to plan. So you can see here at the beginning, it just takes a minute in order to build a model of the environment and then come up with a plan. So the first part of that we're kind of looking at is actually breaking up our footstep planner into this kind of 2 stages so that we can use first a body path in order to get through the world and use this to kind of drive where we determine our contact sequence. Then one of the things that we noticed was in order to actually get a model of the environment, the multisense on the head of the robot just wasn't working while we were moving. The data was just too noisy. So instead we added this Intel RealSense to the pelvis, which we're able to build these planar regions in the world here as the robot's actually moving, and we can use those to plan individual steps. And so if we kind of just do a really quick algorithm in order to pick and place these steps along these planar regions, you can see that it was starting to work pretty well. The robot's not having, right now we have an operator actually kind of confirming every individual step saying, okay, that one's good, that one's good. But it's starting to get to this mode where it can just continuously pick where it wants to step over these cinder blocks. One of the things that we saw, though, is that a lot of these steps aren't what you would call the best location. Some of them are hanging off the cinder blocks due to just noise in the system. So we decided to start looking into this continuous rotation detection and cropping. So be able to figure out actually when you put the foot on the ground, because you don't really have a skin on the underside of these feet. All you can do is sense kinematically the rotation of the foot and then where the center of pressure is. So we're detecting that rotation by kind of sensing the angular velocity and the total amount of rotation. Then we're extracting actually from the foot where that edge of rotation is by looking at the kinematics as well as the center of pressure history. And then we're saying, okay, well, which part of that foothold do we want to throw away? The part that we look at, that we get rid of, is the part where we tried and failed to put the center of pressure. And then we keep the part where we tried and succeeded. And so when we kind of tie that in, it works pretty well. The robot's able to walk over these cinder blocks. So here we've actually told the robot a couple of bad steps along the way directly, saying step here, and the foot kind of rotates on the surface, but the robot's able to pretty quickly adapt and crop that foothold off and keep walking. Kind of the next big part of our current efforts is progress on our robot Nadia. So Nadia, we're aiming it to be this high degree of freedom robot that's relatively lightweight. I say relatively because, you know, those kind of metrics always increase, but also pretty durable and everything. So we've made a lot of progress on this. We're coming pretty close to a fleshed out design for the lower body. Here we actually have about, when I say high range of motion, we're able to hit pretty good. And we've got about 90 degree of total range of motion on the hip ab ad. And then we have about 145 on the flexion extension. while still maintaining about 160 degrees on the knee. So we're able to do these pretty big flexible motions here. Part of that's enabled by our actuators. So we're still using the Moog hydraulic actuator, very integrated smart actuator. And we also designed our own electric actuator for these hip yaw and spine yaws that you see here. And with that, we're thinking we're going to be able to achieve these kind of crossover motions like you see on this far right. We actually have managed to build a prototype of it, and here we've got that prototype leg doing jumping. It was able to jump for about 45 minutes with, I think that's about 125 pounds on there, until eventually the rod end that you see kind of poking out there at the end actually broke. So we've replaced that in subsequent designs, but we weren't really expecting that to be the point of failure. Pretty happy because that means that the shells, the carbon fiber shells that we used weren't. So that's a nice bonus. Kind of the last part of a lot of our work is our exoskeletons. So we've been doing about 10 years of exoskeleton development. We've actually been able to stick with Mark, who you see here on the far left, throughout the whole process, from the Mina V1 all the way to our newest one, which is Quicks. And you'll notice that we've kind of been adding powered joints as we go. So we went from just the hip and knee powered to now, to then in Mina V2, we added the powered ankle. We used that exoskeleton at the 2016 Powered Exoskeleton Competition in the Cybathlon. And then in the newest one, we actually added powered abduction adduction on the hips. And we're really pretty excited to use that in our upcoming projects. So we've got the Cybathlon here in 2020, as well as the Toyota Mobility Unlimited Challenge. We're hoping that by having that additional degree of freedom there, we're able to use some of this sagittal motion to reduce the loading that Mark, our pilot, is actually having to do with his crutches when he shifts his weight from side to side. So we have a great team that goes into making all this work possible. This is actually a year-old picture at this point. Unfortunately, we aren't able to get a new one. And then the nice thing is we're actually hiring. So we're hiring positions for controls engineers for both controls, electrical design, and mechanical design engineers for all of our exoskeleton and humanoids work. And with that, I'd like to thank you all, and I'd love to answer any questions.
All right. Thank you, Robert. Are there any questions from the audience? Let's see. Okay. Yeah, so we have a question from Jonathan Hurst.
Or I'll ask a question here. So this is the first time I've seen, maybe this has happened before, but this is the first time I've seen very clear combination of a electric motor with a hydraulic device. I kind of wonder what your thoughts are on that in terms of the very different dynamics between the two, how they're going to integrate, and also the very different kind of support engineering for the two and how that's going to integrate.
It's a good thing to point out. I think with hydraulic actuators, we're able to offload a lot of the physical design aspect of the actuators themselves to Moog, because if you look at the actual actuators, the sensors and everything are integrated into it. So we're not having to design that aspect of it. We're still having to look at doing the HPU system, the hydraulic power unit, ourselves, more than likely, but that does offload a lot of the really difficult design work. And then electric actuators have come really far in with just the amount of information and amount of available electronics out there to support these kind of actuators. So I'm not too, we've been able to kind of leverage a lot of that work in the development of this one. One of the, I guess, challenging things is you talk about, especially this, our electric one is going to be liquid cooled. So now we're going to have a liquid cooling pump and radiator in addition to the hydraulic pump and radiator on the robot. It would be nice if we could find a nice rotary electric or rotary hydraulic actuator that would fit the form factor that we're looking for, but we weren't able to find a good one that hits the specifications that we needed for that packaging. it is definitely going to be tricky, but I think that there have been other groups that have done that. I'm not sure.
I have a question, Robert. So can you tell us a bit on the EXO side? So you talked about the different versions of the EXO where you were adding additional degrees of freedom. Do you have a sense, or have you studied, examined how those additional degrees of freedom affect the individual's performance, metabolic cost, speed, capacity, and so on?
We have not done any rigorous tests of actually looking at the metabolic costs, mainly just anecdotal. So it's been nice that we've had the same pilot kind of throughout this whole process. He's been able to test all of the different devices for us. And the biggest change that we saw was when we went from having the power to a passive joint at the ankle to having that as a power joint there. So one day when we were testing, we actually went back and changed the power joint to act like a passive spring, and he was only able to complete the obstacle course for the competition once through in about 3 times as long before being completely exhausted. And it kind of is intuitive when you think about all of that, the force that he's having to exert the force with his arms through the crutches rather than through the powered planar flexion in that situation. And so, because we are talking about a device that's meant for individuals who are paralyzed from the waist down, I think that the additional power degrees of freedom have really made it more user-friendly and more usable, especially from an endurance standpoint. Again, that's anecdotal. We have not looked at the metabolic costs. We're not really set up to do that.
All right. So we're about 20 minutes over time already, so I'd like to just go ahead and transition to the next speaker. So next speaker is going to be Danat Kistamakaru, who's going to tell us a little bit about or question the role of metabolic cost in how people choose to walk.
Thank you. Thanks so much. I'm going to turn on my screen. Sure. It is all visible? All good?
Yes.
Well, today I'd like to show you some results of several experimental studies that we have done over the last 5 years that relate to gait parameter selection in both level and uphill walking. And these studies were inspired by some really cool experiments in locomotion, at least in our view. The first set is the studies from Burton and Marina that nicely explained how, from the metabolic landscape shown here, you can predict the preferred velocity given a particular or imposed frequency. And you can actually get these preferred velocity and frequency relationships. And they furthermore very nicely explained that these relationships depend on which gait parameter you impose. Second are the experiments of the group of Max Donovan and Art Kuo. They had people walk while imposing a frequency velocity relationship that was different than the preferred relationship. They call them control or constraint functions. And using these experiments, they showed that subjects are more drawn, at least initially, more drawn to their preferred relationship than to minimize the metabolic cost. And we really like these studies. We have these experiments as a lab demo in our course on the biophysics of locomotion. And in line with these demos, several students chose to do follow-up experiments. And I chose 3 for today to share some results. This is the general overview of the experimental setup. It's pretty basic, besides or apart from the large treadmill. So we have like a really nice large treadmill And the cool thing about this is that we can have a pretty natural way for participants to select their own walking speed. So if they speed up, they walk to the front of the treadmill. We have some kind of feedback system in place that speeds up the treadmill and brings them back towards the dead zone in the middle of the treadmill. So they can very naturally select a velocity. For relevant measure of energy expenditure, we calculate and measure the metabolic cost of transport for level walking. And of course, if you want to climb a mountain, metabolic cost of transport won't bring you to the top. So we have for that the metabolic cost per vertical meter. The first study, we sort of replicated the Snaterson study. The first experiment, we found the velocity and frequency imposed, preferred velocity and frequency relationship, and constructed a velocity imposed and frequency imposed constraint function. So there is no real time to go into details, but the general thing is the following. So we have a constraint function that intersects the preferred relationship in 3 points, namely P3 here, the preferred walking point, which is the lowest metabolic cost measure, and P1 here. And the general idea is that when walking is habitual rather than optimal, people would, when this constraint function is turned on, start walking with a step frequency and velocity that is either around P3 or around P1. But if they would online minimize metabolic cost, they would end up somewhere in the preferred walking point. So let's just see what subjects do. Here I have one subject. I hope you can all see this. So this is one particular subject. We have a velocity imposed constraint. After 60 seconds, we turn on the constraint function. So this blue dot is the participant's step frequency and the velocity of the belt. And you see that basically pretty much straight after we initialize the constraint function, it jumps towards this intersection here. And basically the same is true when we impose a frequency imposed constraint function. So after 60 seconds, the constraint function turns on and then people start walking at this intersection here. But then we thought like, yeah, but maybe it's just really hard to walk here. Maybe there's just something really funny with this constraint function. So what we did is we had another experiment where we provided the participant with feedback about their preferred velocity in this point, and we just said to the participant, okay, just walk on this velocity. And then again, we turned on the feedback or the constraint function. And this showed that the participant was able to walk at just around the preferred walking point. So the question is then, what's the general results? We found that all subjects were able to walk at the preferred walking point with the constraint function turned on, and when given feedback about either the preferred velocity or the preferred frequency, that the constraint functions, importantly, did not change the metabolic cost of transport. This is with the imposed constraint function and feedback, but that none of the participants walked on the preferred walking point when the constraint functions were turned on, but they were allowed to do whatever they want. And as such, they use quite a bit more metabolic energy than is necessary. So then we thought, okay, but what about the selection of gait parameters under completely novel circumstances? So we did like quite a large experiment in which we also addressed slow and fast adaptation. But the main experiment was the following. So we had participants walk with 2 kilograms, a mass 2 kilograms at each of the ankles. We had them walk for 2 minutes at 4.5 kilometers an hour, and then after 2 minutes we bumped up the speed to 5 kilometers an hour for 36 minutes, and then we looked at the adaptation in step frequency and the metabolic cost. So you see that here, the step frequency. So you see this immediate response, very fast response, which is quite similar to what is known in the literature to to this perturbation. And then gradually over time, you see that the step frequency is diminishing. So there's an adaptation towards a lower step frequency. But if we then look at the metabolic cost of transport measured at several of these instances, we see this basically all over the place. So some go quite a bit up, some go about the same, some go down. So this, in our opinion, means that the selection of this step frequency is not driven by the metabolic cost of transport. So then we thought, well, maybe the differences in metabolic cost of transport are just not high enough. And so we thought about, okay, but what about the gait pattern selection when walking uphill? So we had an experiment which we controlled also the angle of the treadmill. We measured the preferred velocity at a bunch of different slopes, up to 80% or 10 degrees. We measured for a bunch of velocities at each slope, the oxygen consumption. And then our main experiment was that we said to a participant, well, why don't you just walk 100 vertical meters? We provided them feedback about the amount of vertical meters traveled, and you can just do whatever. You can just go up or down in slope, or you can just speed up, whatever you want. And then the question, of course, is what these participants do. Here you see the outcome of the first part of the experiment. So the velocity, the preferred velocity as a function of the slope, and the metabolic cost per vertical meter. And we see that the most optimal slope is around 10 degrees. But what participants did was consistently choosing a much lower slope. And we also checked whether the initial slope that they started on influences result, which wasn't the case. So that brings us to the general discussion. So based on these three studies and the other studies that we have done, we see that metabolic cost is not a key determinant in gait parameter selection, at least not on the short term, and not in novel situation. And step frequency adaptation, but without an accompanying change in or lowering in metabolic cost. And also not in choosing the optimal slope, because the preferred slope is by far not similar to the optimal slope. And with this, I would like to thank all of our students that participated in performing these experiments, our tech guy, Richard Kasius, and my two great colleagues, Martin Colbert and Knut van Zust.
All right, thank you, Donat. I guess I'll be the first to acknowledge that we were a little bit creeped out by your background. I'm assuming that was on purpose, but are there any questions? Let's see, I don't. Okay, so we have a question from Max. Go for it, Max.
Hey, Donat. Yep,
Hi, Max.
super creepy by your background, super creepy. Okay, can you go back one slide?
I can go back one slide, but of course.
Okay, so this conclusion, metabolic cost is not a key determinant in gait parameter selection.
Mm-hmm.
I feel like, you have a responsibility to then explain you have three, interesting studies, fairly unique, maybe possibly explained in other ways, but then there's, many other studies that reach the opposite conclusion. So what is your explanation for them?
Yeah, I'm not really sure. Maybe it's a sort of coincidence. I am not really sure. I find it a really hard question. We have had many discussions in the past about this, but this is just basically what we see. And there's another thing that doing these experiments we also saw. Like, for example, we saw that the variability within participants of choosing their preferred velocity was way smaller than the changes in metabolic cost. So over a very large range, we saw basically the same metabolic cost where people are very strict, always choosing the same preferred velocity. So yeah, I'm not really sure. not really sure about all the other stuff that's out there, but when we do this, we just consistently see that when you look closer, there is just not really many. Yeah.
If I could just make a statement rather than ask a question, I think, what we should responsibly do as scientists is try and unify these, as opposed to one camp saying it's not a key determinant. Here's a handful of studies that show that it's not. And then another camp saying it is a key determinant, and here's a handful of studies that show that it is. Like it seems like responsibly we have to try and explain as much of this data as we can, as opposed to just reaching different conclusions.
Yeah, no, I fully agree. But you also just want first to get just some data out there, just in novel circumstances, just to see what's going on, and maybe coincide. We saw today a nice study where we also looked at the sum squared muscle activations. We know that from Friedel that if she doesn't incorporate the sum squared muscle activations, the outcome of her modeling is not what you can see in real life. So yeah, I think this is just important, just to get a good idea about under what circumstances we find that metabolic cost is really driving gait parameter selection.
I agree, but I'm taking particular issue to what is above the numbered list, right? Like the way you said that there is like, hey, in some cases it doesn't explain it, but what's above that numbered list is that it's not a key determinant in gait parameter selection.
Yeah, because that's basically
Sounds
what
like
we
it
see
never
in
is.
all our studies.
But that's beyond that claim seems to be beyond a
So
handful.
it sounds like part of the issue is the nuance in your claim, right? Making a claim that seems to be generalizable broadly, as opposed to taking account of all things that have been shown across multiple studies, right?
Yeah, it's a nice provocative.
I assume so.
But so we've done several of these studies. We also have done, in addition to this, constraint optimization, walking on these treadmills, and there we also just don't see it. The people just don't seem to be sensitive at all to metabolic cost, even when we just bump it. And we also, for example, biking is another very good example. So there it is about just trying to pump out as much energy as you can, while, for example, in a sprint, and we just know that people consistently do not choose the cycle frequency at which they use for a given power output, the least amount of energy. They just don't. It's very consistent.
Yeah.
All right. Max.
Well, I should let others talk.
Okay. So really far over time here, lots of questions, lots of hands raised. So obviously this is a topic of general interest to the audience. Danat has purposefully been a little, well, not a little, but quite provocative with the statements he's making. I'd like to at least do one more question here. Peter, your hand was the next one I saw.
Sure. So I just pulled up an old paper from 1995 by Minetti, which was talking about mountain paths, and it had an analysis of what should be the most economical as well as the preferred or the observed slope of mountain paths. And it found that both of those coincided and were at a number of 25% slope, which is more like 14 or 15 degrees. And I'm wondering if you can just comment on why you think your constant slope treadmill results, specifically the 100-meter climb version, which sounds like mountain climbing to me, would or might show a different result from that sort of real-world phenomenon.
Yeah, that's a very, very good question. So yeah, we were not, at least in a lab situation, not able to replicate this. And one obvious thing may be that our subjects were just not used to walking in a mountain, which is not a strange assumption, knowing that these participants were all Dutch. And the only way to go up in Holland is to go down first. So that could be one thing, but I'm not 100% sure. So if we do this, and we have measured it quite extensively, and we've measured each participant several times, we just don't see it. And yeah, together with the other experiments we've done with slope walking, yeah, we are just not able to replicate the finding of Minetti. Oh, the only thing is we see clearly that the higher the slope, up to the maximum of 10%, 10 degrees or 18%, we see a decrease in metabolic cost per vertical meter traveled. But yeah, that's the only thing we can do. Like in our lab, we have a very nice big treadmill. They don't seem to be uncomfortable walking on it. We just don't replicate it every single time. We just don't. So I'm not sure.
Okay, with that, so for those who still have questions, a number of questions remaining, I'd like to suggest we move over to the spatial chat room 9 to continue this conversation, because there are people who have posters during this current time period. So Aaron, I don't know if you're still there, if you'd like to make any announcements about follow-up or startup time for the next session.
Yeah, so I think we'll shift it back to 5:20 maybe. So give us a 40-minute poster session. The poster sessions keep getting shorter and shorter, but the discussions have been good. And yeah, so again, rooms 1 through 8, there's poster sessions. Room 9, follow up with any of the speakers we just saw. Room 10, totally free form, or you can hang out here. For those of you on YouTube, I'm going to end the live stream now, and we'll start a new live stream for the final session in 40 minutes from now, which is 5:20 Eastern time. All right, see you guys.